Hello guys, this is Alan. I'm sorry I cannot participate the meeting in person, but to present my presentation in person to you guys and ask the question and discuss with you. So here I am. I try to use the video mode to tell the outline and the concept for my topic. So starting from the last topic we have just stopped at the principal plane. We will now use the phasor notation to give you guys a brief review. So starting from the curl, we know that the curl vector, because we suggest that the electric field and the magnetic field both have the form of exponential to the minus jk omega z, minus jk z. Thus, this term gives the gradient of the exponential term, and thus drop down the minus jk. And with the minus jk, the j will eliminate with each other and then left the minus sign. Thus, we have the minus sign here. Similarly, this can be applied to the electric field cases. Thus, we will have these two relationships. In this relationship, it's kind of easy to show that the dielectric term, that the electrical displacement, electric field, and cross k cross E equals to the H. Note that the K and E both are on the same surface, same plane of same plane. Yeah. And because we are talking about an isotropic medium, which suggests that D equals to with the polarization. And this is on the symmetric structure, which suggests that along the electric field, the dipole moment may not be parallel to the electric field. Because when we're talking about the isotropic system, it's usually that it will be parallel to it because it's an unsymmetric material. So that gives the displacement and the electric field both are not parallel to each other. And thus we will show later that the K is not parallel to the S, which is the Poynting vector. Because we will have a rigorous picture about it, especially in the uniaxial cases, which we will show that this Poynting vector, which actually we have two Poynting vector, which is one of it, it's as what we expected parallel to the K, but another it's not. This will be shown in later. And just to special mention that DESK lie on the same plane, which is called the principal plane. Thus, starting from the wave equation, we'll get a Helmholtz equation. And then with some mathematical tools, we may found that the Laplacian operator can be expressed in this form. I suggest we are in a source-free condition, which suggests log equals to 0. Thus, this term will be eliminated. And then using the same techniques that we have used in here, there are two minus jk term drops. And then for the term here, we'll just simply derive it. K equals to the 2 pi over lambda, n equals to omega over lambda f, which suggests that it's omega n times c. And n is the relativity index, and the c is this term. Of course, which as shown here, it's not in tensor form, but it's just easier interpretation for you guys. And then this would be this term. And what this term is actually the epsilon. And because we have the square of it, thus this term suggests a permittivity tensor of it. So just some cleanup, we get this equation. And then now the problem is how to solve this. We'll introduce some linear algebra concept and use it and try to express this in a matrix term. So we know that this will be equals to this term. Thus, we will just examine the first term. Consider the first term of it, minus k2 squared minus k3 squared, which is exactly the component inside the first element of this matrix. And then the extra term comes from this term, which is exactly, we know that k squared equals to, if it suffers from a refractive index, then it's this term. And then along this direction, it's the epsilon 1, which we have the index 1 for it. Now, it's time to solve for this equation. But for us to have a non-trivial solution, linear algebra tells us that this matrix needs to have a determinant equals to 0, which suggests that it has an inverse matrix. And thus, we will get a non-trivial solution. So I would like to emphasize here that remember our ultimate goal is to have the electric field. And now all the steps that we are doing now is just for this purpose. Okay, so solving for the matrix determinant equal to 0, we will get this, just some hard work. And then after divided by k0 to the power of 4, we'll get this kind of solution. And then my question is that I cannot conclude this equation into this solution. That's my questions here. And if you guys have any idea or any solution to it, please contact and message me, because this really struggles me for lots of days. And however, if we successfully get this equation, which is Bernal's equation for normal modes, then this will gives us a K surface, which is shown in this. So let's take a deep look about this solution. So consider K0. Actually, this is 0, remember, because we are consider the 0 in vacuum states, the K vector in vacuum. And this term equals to this one. So the K0 square has the information about the frequency component. And then the refractive index is the environment condition. As for the U, what is U? U is exactly the direction of the propagation. And then suggest that it's a unit vector. So this is the direction that we give it, that we suppose we give a direction, and then we hope to get the K value of it. So what we see, N is the environment, U is just manipulated by us, which suggests that for a given frequency component, which is the temporal mode. For temporal mode, there are multiple spatial mode, which is K. And all the spatial mode construct the K surface. So consider, let's take the most general cases, that is the biaxial cases. And just a quick reminder that all the coordinate talking about in here, we are talking in principal coordinate system. We suggest that epsilon tensor of it, which only has values on diagonal term, thus the electric field on any component will only suffers from one index instead of three. Thus, consider a wave propagating in y direction. What this diagram suggests is that it suffers from two refractive index. Let's decompose into a diagram view. So for a wave propagating in y direction, the normal mode for it's along the normal plane. And then the two solution we may have is the Z and the EY, actually. EX component. And because it suggests that the EZ suffers from the index NZ, which suggests that it travels with velocity c over nz. And similarly, the x component travels in c over nx velocity. So after a period of time, the z may travel to here, while the ex component will travel to here because they have different velocity. And also, there's also a characteristic for these normal modes. That is, there are two stuff remains the same. First is the velocity. They all travels in constant velocity for their own. Also, their direction remains the same. It's always this direction. Consider another direction that's this. Consider another mode that's in this. Then the velocity is not constant because it varies, right? When these two, then the direction may goes another way. And then the direction is of, and then the direction of it is of course not the same because the two components of it just varies as time goes. So so another characteristic for the normal mode is that the velocity and the direction remain the same. All right. So be sure that this is just an octet view of the K surface. And let's start from the isotropic. Isotropic is kind of reasonable because it's just a sphere, which means that given any K vector, it would seize a index n, refractive index n. It's what we expect because for any direction of the electrical magnetic wave inside an isotropic material, it always sees the refractive index n. However, for the uniaxial cases, which we will derive it in more, which will show that actually the K surface consists of a sphere and an ellipsoid, which means that for any direction inside the uniaxial material, it will always seize one refractive index that's a naught. This is really important, and we will give a more rigorous proof later on. And as for the biaxial cases, it's just as shown here. And to see that there are 4 points that you'll see that they only suffer from one refractive index. And along these 2 points, it constructs a optical axis. That means for the propagation that's parallel to I didn't mute myself. For optical that's parallel to the k direction, you only see one refractive index, which means it's just as the plane wave that we loved before. Okay. So, and also I'll give a quick reminder that there are 2 optical axes for the biaxial, but there are only one optical axis for the uniaxial cases. So, yeah, starting from the Fresnel equation for normal wave, given a direction u, we may find 2 meaningful solutions, which are the normal modes. But if we only obtain one solution, then that's optical axis. And recall that I have emphasized before that all we have done is to solve to get the electric field. So the K is not the final goal of us. The final goal is to plug it back to this equation. And then to solve it, we will find that the electric field is proportional to this vector. Combined with Fresnel's equation for wave, we will find that the corresponding 2 normal modes for the electrical displacement, they are perpendicular to each other. And actually, I'm quite struggle to give a vivid proof of it. But for the physical interpretation, it's kind of intuitive that given any direction k, it may have a surface that's normal. It might have a plane that's normal to the k vector, and it's expanded by 2 vector, which is the 2 normal modes of the electrical displacement for it. So if you guys have any idea about this, please contact me. I will be really happy. Thank you. So yeah, okay, so let's now continue. So now we have just interpreted our wave equation as physical, just directly. And now we will just mixed with some linear algebra concepts. So starting from the conclusion we had before, with some common sense, we will get into we can find that it can be expressed in this form. If we take this as a projector, then we will find that it will just project the electrical displacement onto a plane with eigenvectors and the corresponding eigenvalues. So just what I've shown with a U, and then for any electrical displacement, it would just project it to the plane that's perpendicular to the propagation direction. So for any component that's not parallel, then it will be eliminated. So this is kind of a projector concept, right? You project it onto for a given vector, it projects it to here. Well, this is orthogonal projection, right? And this is just the index ellipsoid that we have discussed in previous lecture. So I believe you guys still remember. And then now, with all the general case discussed, now we will start to talk about special case, which is the uniaxial cases. So starting from the definition of it, we know that given 3-coordinate system, choosing the principal coordinate system gives us the epsilon to left diagonal values. And then this would result in 3 refractive index. And then the uniaxial cases is just that 2 of them are the same and 1 of them are different to others. So the 2 remain the same. It's kind of ordinary because the majority of them are the same. And then the one that's left different is extraordinary. It's so special. So the term here stands for O instead of 0. Please take into deep consideration. And then the conclusion that we have shown before, that for us to have a non-trivial cases, we have the determinant equal to 0. Thus, we have this conclusion. And then with some mathematically derived, we will come into this conclusion. And we would magically show that this can be decomposed into 2 components. And then the first component shows that the k equals to n ordinary times k0, which means that for any direction, for any propagation direction, you will always get a solution that's n ordinary times k0. That means that for any direction, it would always seize the same refractive index. This is actually the behavior of the isotropic material. But besides the solution, we have another solution, which is the ellipsoid. And this may be hard to interpretation. So in our cases, we would like to suppose that kx equals to 0, which means that k equals to ky squared plus kz squared. Okay, so if we see it in a k2 and k3 axis, we will see that a circle with an ellipse. So it's kind of reasonable, right? And then, so now we'll just do some derivation. So we have this term, right? Because we assume kx equals 0. And then we'll divide it both with k0 squared. So now we know that k equals to ky squared plus kz squared. K squared actually. And with the refractive index taken into consideration, the y-axis is the ordinary axis. The z is the extraordinary. Thus, we have this conclusion. So, continue the equation we have here. The z-axis is the extraordinary. We have this conclusion. And if we divided both sides with n, then we will come into this conclusion. So it's kind of reasonable that we will see from here that it's just a sinusoidal term. So we would like to say that why not we just let n ordinary over n to be sine ne equals sine, which just give us this solution. So now we would like to give a physical picture about what the theta is. So what exactly is theta? Given a optical axis, and then the k would be the theta would be the optical axis. The k have the theta angle with the optical axis, and then with the solution that we have shown before, that if the k is along the x direction, along the optical axis, it's actually ordinary, and otherwise it's extraordinary, right? And along these are the n theta. So I would like to go back to this and give a screenshot. So let's compare. So this is the more 3D view of it, and this is the 2D version. Okay, let's see. What this plane is actually this. So here we will get the same. We'll get the same picture here. So if we, as we have said before, that they are ordinary and extraordinary. So consider ordinary mode. It's actually just exactly consider a k. This to be a, to consider k. Then it's actually just exactly as what we have in previous discussion. But if we have another k that is extraordinary, then the D and E will not be parallel to each other, because it's not spherical that in any direction it will be the same. It's instead an ellipsoid, so it will be different as different direction goes on. And that's why the D is not proportional, it's not parallel to the electric field. Yeah, so okay, so here is just a just a kind of physical intuition to provide it to you guys. And just to special mention that, remember that all we have done is to get the electric field. So please remember to plug back the electric field after you solve for the K, the normal modes. So just to conclude uniaxial cases, that given a electric field, given a propagation direction K, then we know that because the linear algebra view, it says that it would give us two components. That's perpendicular to each other. And I think I forgot to mention that that the corresponding eigenvalue NA and B is actually exactly the length of the long axis and the short axis. And this is stated without proof. So if you are interested about how to prove it, you may refer to the textbook, the reference one. Okay, so back to what we discussed here. So given a vector k, it would have a normal plane that is expanded by two normal modes. And since we are talking about uniaxial, so this would correspond to DO and DE. And just what I have said, that for the ordinary cases, any direction of k suffers the same refractive index. Thus, it's actually just the isotropic case. So we will see that in that case, the k is parallel to the SO. Why? And why? Because we can show, and also this is without proof, that delta k dot S equals to 0, which suggests that given a k surface, then the S will be along this direction. And because thus, the picture will be better. Thus, if we give an isotropic, which is normal mode, actually not isotropic, we would say to it to be ordinary, then the S will be along the axis. So propagating k. But if you are ellipsoid, then k, this is the S, and they are not parallel to each other. Yep, and that's all. Yeah, so that's why we will see that k is parallel to S0, but not parallel to the SE. And for the extraordinary cases, because you are not a sphere by ellipsoid, thus the DE would not be parallel to the electric field. And this is all that I would like to say for this part. I think I didn't left a lot of stuff. And okay, so just to mention that, what is K-surface? K-surface is just given a temporal mode omega, then you have several solutions, and those solutions forms the K-space, which is the K. So given any direction, you found the corresponding K value. All right, that's a sum up. And if you guys have any ideas about how to derive the Fresnel's equation for normal modes, please contact me. And if you have any ideas about how to combine the solution of the electric field and the Fresnel's equation for normal waves to get into a conclusion that the two normal modes of the electrical displacement would be perpendicular to each other, tell me, because I have struggled this for several days, and yeah, but with discussion with my teammates, we only come to conclusion that we have a physical intuition, but not a rigorous mathematical proof. So that's all for me today. Thank you.